Hey everybody, welcome to this video where we will be showing you the various ways in which you can solve the Collatz Conjecture exercise in F#. There will be 4 different approaches that we will show you, and we'll showcase the benefits and the downsides of each approach so that you can compare them and decide for yourself which one you like best. In case you don't know, the Collatz Conjecture is a mathematical conjecture, so it's unproven. But it says that if you take a positive number, so greater than 0, there is a formula that you can use and it will always end up with 1. And the formula is, if it's 1, you're done. But if it's greater than 1 and it's even, what you then do is you continue the same process but with the number divided by 2. And if the number is odd, you'll multiply it by 3 and add 1. And if you apply that repeatedly, in the end you will end up with 1. So the goal of the exercise is to determine how many steps does it take for a given number to reach 1. And that is what we will be solving in this exercise. Let's look at what we are expected to implement. We are given this stub file. It's a module with a single function called steps, which calculates the number of steps. And it does that by working with a number that gets passed in. So there's a single parameter called number, it's an integer. And it returns an int option. So what does this option thing mean? Well, the Collatz conjecture is only defined for numbers greater than 0. So if we pass in a number of 0 or a negative number, there's nothing that we can actually calculate because it's not defined for that. And we could return some magic number like -1 or something like that. But a much better and more idiomatic way to do that is to use an option type. So an option type is basically one of 2 values. Either it's none, which means that I couldn't do anything with it. There is no result. You can sort of, this is sort of similar to what null is often used for. So the absence of a value. And then the other way that an option type can be constructed is via sum with a value. So you can see it like it's wrapped in a sum value. And then the caller has to explicitly check if it's either sum with a value or none. So you can indicate by the return type whether or not the computation was successful, and that's an option type. We can look at some of the tests. We can see here that steps of 1 is sum of 0. There are 0 steps to reach 1, but it's still a valid number. So we have it in a sum value. Same goes for all the other numbers. And then we have a 0. So 0 is invalid, and then we return none. And the negative number is invalid, and we also return none. And these are the tests that we will be solving. The first approach that we will be looking at is an imperative version. It's not actually a functional version, even though F# is a functional first language. This approach is not necessarily idiomatic, but I do want to show you because it's absolutely fine to use mutation in F# if it doesn't influence the pure function semantics. So if you call the steps function with a specific number, you should always get the same result. And if we only use mutation within the function, that's totally fine. If we don't depend on global state, it has the semantics of a pure function, so it's actually fine. We'll show different approaches later that do it in a functional way, which are preferred, but I still wanted to show you the mutation version. So let's get down to it. The first thing that I wanted to do is to handle the error case, so the edge case, which is if the number is less than 1. So if the number is less than 1, then we can't compute it, and as told, that's where we would need to return none. So what do we do in the other case? Well, for now we'll just also return none, and it will have some failing tests, but that's fine. We should have 2 tests that are passing, the ones about the negative value and the 0 error. Okay, cool. So then we have to implement the algorithm. So we will have a number that we will continually update. So we have to have something that's mutable. And in many languages, you could reuse the parameter value, but we can't in F#, and I also wouldn't. So we have to create something new. So we're going to say that current number is equal to number. Only this doesn't really work because we can't update values by default. We have to explicitly opt into mutability. So we're going to say let mutable current is number. So current starts out with the value of number, but it's mutable. Then the second thing that we have to take care of is steps. So the number of steps. So it also has to be mutated because we're going to increment it. So we're going to say let num steps equals 0, start with 0, and then we get to the meat of the algorithm. So we're going to continuously do things until we reach 1. So that sounds like a while loop to me. So while current is not equal to 1, then we do something. And that something is actually, we have two cases. If the number is even, we do something, and if the number is odd, we do something else. So determining whether or not a number is even is commonly done via the modulo operator. So if we do current modulo 2, so that's the remainder of dividing by 2. And if that is 0, then it could be divided by 2 and it's even. So if current is even, then we have to update it. And we shouldn't be using the equal sign, because equal sign is for a new binding. We want to update the value within the mutable binding. So we're going to do the left arrow operator, and we're going to say the new value of current is current divided by 2. So in the odd case, we update current to be current times 3 plus 1. So now we have the whole logic of the updating of the current value done. We still have something left to do, which is to increment the number of steps. So num steps plus 1. And then we return sum of num steps. And that's the entire algorithm. So let's go through it slowly. We start out with defining a mutable binding current that is starting out with the value of the number. The number of steps is equal to 0 because we haven't done anything yet. And then we keep on looping until the current number is 1. And if the number is 2 is even, then we divide it by 2. If it's odd, we multiply by 3 and add 1. And we will increment the number of steps. And then in the end, we have been successfully able to calculate the number. Then we'll return the number of steps in a sum value. So if we run this, this should solve all the tests. And it passes all the tests. Yeah. So that's our mutable approach. It's fairly typical mutatable code, but let's try out some different approaches too. Let's try a functional approach to this problem. And the one that we will be using is one in which we do manual recursion. So we will be writing a recursive function. So to start out, we will define a function called do steps, which will be our helper function. This is a very common pattern where you have a function that calls a helper function to do the actual recursion. We must make it recursive. So we have to add the rec modifier. And then that will take 2 parameters. So the current number, which is an integer, and the number of steps, which is also an integer. And it will return an integer. So we don't return an int option because we will do the error handling within the steps function itself. For now, let's think about what the do steps function should actually do. So if the current number is 1, then we are done and we can return the number of steps. So let's start with that. So if current is 1, then we return number of steps. The next case that we need, I say 1, but I should actually be writing 1. Else if the current number is even, so we'll do the same modulo operator thingy, then what do we do? So this is where we do our recursion. So we're going to call the same method. We'll be calling it by changing the current number to current divided by 2, which is the rule for even numbers. And then we'll be calling it with the number of steps plus 1, because we have done a single step. Then if it's not 1, not an even number, it must be odd. So we will be doing a recursive call again, but this time we do update the number to current times 3 plus 1, and then we'll increment the number of steps by 1. And that's our functional implementation, our recursive implementation. So we stop when the current number reaches 1. If it's even, then we do a recursive call with an updated number and an incrementation of the number of steps value. And we do this a similar thing with odd numbers, where we have a different algorithm to change the current number. Then all we need to do is to combine this in this function. So we're going to do if number is less than 1, then it's none. Otherwise, we'll call our helper function. The initial value is the number that gets passed in, and the initial number of steps is 0. And we have to wrap that in a sum value. And this should be actually be passing all the tests. So let's run it. And it does. So we have a recursive algorithm here. We explicitly have if, else, if statements. We could write this in a match statement. I think it's just as clear with if, else, ifs, but feel free to disagree. You could, for example, have these be on separate lines, which can somewhat improve readability. That's one option. We could make this private, because we probably don't want to expose this. So private. But what we also can do is we can change this to be a nested function. So we'll copy this within the steps function. And this, to the reader, this signifies that the doSteps function is just there to help the steps function to return its value. So it's no longer visible outside of the steps function. And that's also a very nice way to show that the outside world, that this is only there for local purposes. For this approach, we will be using a slightly different approach, where we will be generating a sequence of all the numbers that are in the Collatz Conjecture steps. So if we have a number 2, then we have 2, 1, and then we have the end. So, and then we can count the number of elements within the sequence to get the number of steps. So somewhat different approach, but let's see how that works. So we'll define a helper function called Collatz sequence. It will take a current number, which is an integer, and it will return a sequence of integers. So let's see how that works. What we're going to do is we're going to use this the computation expression, the sequence computation expression. So we're wrapping this in a sec, and then with curly braces, and then we're going to say if the current number is greater than 1, then we're going to return something. We're going to return all the steps up to the number 1, but it includes the first one, so that will still give us the right number of steps. So this is our terminating condition. If the number is less than or equal to 1, it should be equal to 1, then we stop. If it's not, there are two different ways in which we can solve this. There's an even one and there's an odd one. So if current modulo 2 is 1, that is even, then we have to do something, and otherwise we have to do something else. So what do we have to do? So we have to recursively generate this sequence. So what we can do is we can actually say, we can do yield with an exclamation mark, and we can say, hey, we're going to yield all the elements that are passed in as the argument. So I'm going to call Collatz Conjecture, so the same function, but I'm going to do it with current divided by 2. So the else case, we do something similar. We do current times 3 plus 1. So let's take a moment to see what this actually means. So this is saying, if you call this function with current greater than 1, we'll do a check. If the current is even, then we will yield all the elements that are in the Collatz sequence starting from this number, and otherwise we'll yield all the elements starting from that number. And this is all good, but we did forget one thing, because we have to yield the current number too. So before we will yield the rest, we will yield the current number. And if we now run this, this will generate a sequence of all the numbers. So starting out with 2, this will be greater than 1, 2 is greater than 1. We're yielding 2, and it's even, so we will be yielding it to Collatz sequence current divided by 2, so that's 1. Second step will be here, and then its current is 1, so this doesn't match. So it's an empty sequence, and then the this means that this will be, the previous call will have this be an empty sequence. So we will be yielding an empty sequence, which is nothing. So we have just yielded the single to value, and that will be, well, of length 1. So that's the final thing that we need to do. Within the steps function, we need to call it. So first, let's get the error handling out of the way. You probably know the drill by now. Otherwise, we will call Collatz sequence with the number, and then we have to count it. So we're going to do sec.length, and then finally we have to wrap it in a sum value. So we're going to pass it to sum, and we're going to run the tests, and they all pass. So you can see here that this approach is somewhat different than the other approaches. We're generating an actual sequence and then counting it. And we are using a sequence expression here with yielding values within the sequence. And we now have a nice and working version. We could theoretically also move this to be within the steps function with proper indentation. I somewhat dislike this because I find it a bit much. It's harder to read. And in this case, I would actually prefer it to be outside because it's not just usable from within the steps function. If you wanted to work with the Collatz sequence itself, you could reasonably use that function. So I'm going to leave it outside. The final approach that we will be looking at is one that is very similar to the sequence expression one, only instead of using a sequence expression, we will be using sec.unfold to generate the Collatz sequence. So let's define a helper function, Collatz sequence. It will take number as an int, and it will return an int sequence. Okay, and then we have to call sec.unfold. And sec.unfold has two parameters. One is a generative function. That's a bit more work, so we'll discuss that later on. And the second is the state. And state is, it will be our current number. So we start out with the number, and then we will change the state based on the algorithm that we by now probably know quite well. So the generator function, let's look at it in a bit more detail. It's a function that takes a state, so that's the current number, and it returns a tuple option. So quite a bit. So let's just write it out, and I'll explain what we need to do. So we take state, so that's the current number, and what sec.unfold will do is if you return sum and then the tuple, the first value that you return in the tuple is the value that gets returned at the end when we are done, and the second one is the new state. So, and if you return none, the looping stops. So let's see how that works, and then we'll explain it in more detail. The easiest thing to do is we'll just check if the current number is 1, which means that we have to stop executing, which we signify by returning none. The second thing that we need to handle, if current modulo 2 equals 1, so this is the even case, and maybe for readability we'll put it on separate lines, then we have to return the sum value. So it's a T state option. So the first thing that we return is the value that will be returned when this sec.unfold function finishes. So that's the current number. And the second value is the new state. So what we have in the second value will be the current value in the next iteration. So we're saying current divided by 2, and then we wrap this in sum. And we'll do the other case too. So the odd case will still return the current number, and the next value is current times 3. So first we will check if this all works, and then we'll go through it in a bit. So let's get the error handling in the steps function handled first. So if number is less than 1, then return none, else we'll return class sequence number. And then we'll do sec.length and wrap it in sum. So same logic here. in the we are generating the sequence of numbers in the Collatz sequence, counting them and wrapping them in a sum value. So let's see if this works, and then we'll try and explain this a little bit. And it all works, so that's good. So maybe it's best if we just mentally step through this with a specific number. So let's start out with Collatz sequence 2. So number is 2, initial state is 2. This means that this function gets called with the value of current being 2. No, so 2 is not equal to 1. 2 is even. So, and then we're saying sum current divided by 2. So this is saying, hey, this is actually a valid result. So you have to keep track of this value later on and then return it. So you can sort of think of this as sec.unfold having some bookkeeping, where the current value is added to the list of values to return. And then when in the end none is returned, it will return that initial that bookkeeping list of numbers. So initially the list of numbers to return is empty, but after this call, it will contain just the current number. And then we're saying, hey, for the next time that you call the lambda, use this current divided by 2 value as the current value. So current was 2 divided by 2 is 1. So the next iteration, current is 1, and we hit this. And this says to unfold, hey, we are now done generating the values. Just return all the values that you have marked to be returned. And in our case, that's just a single list element, which is the element with 2, the list with element 2, and that gets returned. But you can see that if you have multiple calls where you return some, the list of values to return will be larger, and then in the end that will be returned. And this is how the Collatz sequence works. And it's a very functional way of thinking. It's something that you have to get used to a little bit, but once you do, it's a very easy way to basically write a while-like loop in a functional way. So which approach should you actually be using? Well, it sort of depends on what you like. I think the mutating version is probably the least idiomatic F# version, even though it's still fine. So I would argue that maybe that one is not as suitable as an option. But the other ones, a manual recursion version is often to be sort of like a last resort. Whereas I have a preference for either the sequence expression or the sec.unfold, where it could be argued that sec.unfold is harder to read if you're not used to it than the sequence expression. So I would say if you're comfortable with sec.unfold, use that version. Otherwise, use the sequence expression version. So that would be my recommendation. But if you feel like you prefer the explicit recursion version or even the mutable version, they're all fine. They're basically excellent ways to solve this issue.